Hi, this is your video on electron configurations. I had promised these to you, so I'm going to try to pull them together. This is actually my third attempt, so hopefully this one works. So what I want to do is start by giving you a reminder of some of the atomic theory stuff we did in the beginning of the chapter. I won't spend a lot of time because there's videos on that also, but just to remind you, if we talk about the atomic model and how this all relates. So if you remember back to the Bohr model, let's get a pencil that actually works. Okay, we're going to get back to the Bohr model, and we're just going to remember that we have a bunch of protons in the middle of the nucleus, and we have some neutrons, etc. And you have this nucleus, and that in the Bohr model, which is what we would call more the planetary model, the idea is that these electrons, and this is obviously not to scale, are going to be in these fixed orbits rotating around the nucleus in this planetary type model. So these individual shells that when you take this to the more advanced the more advanced models are representing what we would call the shell or the principal quantum number. So just imagine that we have this thing called n, and n can have values of 1, 2, 3, 4, etc. So each of these levels represents a shell or an outer level, right? And this is going to be important in a minute. Within each individual level, you have these subshells, and these subshells have names. And so we're gonna, this is just the reminder to get you kind of grounded in the terminology and what we're trying to do. So these subshells are these three-dimensional structures that are existing within these individual shells, and they're very hard to draw, so that's why I don't actually draw them. But that's where that document that I had given you in class is helpful to explain this. So if you remember that I said these shells represent these orbits in this sort of planetary model, and these individual shells can have a number, and actually is also referred to as the principal quantum number, but we'll call them a shell number for now, is these planetary orbit ideas. Within each individual shell, we have what's called a subshell, and these subshells can be referred to by either a letter or a number. This is a more of a Chem 1 concept, but to understand that these subshells can also be referenced using a letter called L, which is your angular momentum number, or angular momentum quantum number. And I'm only explaining this to you just so you can kind of see how this stuff goes together. So we talked a little bit about the individual subshells, and they have specific shapes that have all been determined by using some very complicated equations, and solving the Schrodinger's wave equation. But just for the purposes of just trust me on this, I'm going to tell you that the s orbital has a L angular momentum number of 0. The p has a number of 1. The d is 2, and the f is 3. And the reason this matters, and this is really a Chem 1 concept, but I wanted to show it to you just so you could see how this all plays out. We know that N, L has to basically be less than or equal to N. Okay, now let's talk about this first, or N minus 1. So what this really means is if you were to take the shell number N minus 1 and find that that's 0, therefore, the only subshell that can exist in a level 1 would be your 0 or S. Same thing over here, minus 1 equals 1. It can be greater than or equal to, you can have a P, which is a 1, or an S, which is a 0. Over here, this is 1 equals 2. You can have a D, a P, or an S. And here, equals 3. You can have an F, a D, a P, or a S. So this is really not in the scope of the class. It just does help you understand where this is heading for, and it maybe helps you kind of get that picture in your head for when you get to Chem 1A and you need it. So I'm going to go ahead and erase this because this isn't really relevant for the class other than to explain to you where this comes from. So that doesn't confuse you. We're going to get that to go away right now. What you really need to take away from this is going to be really just how to use this chart. And this chart's going to be really important. Okay, so this explains how the individual shells, L, and relates to your subshells, which would then be L, which we're not going to worry about that right now. And they each have these individual shapes. So then you go to your subshells, and each subshell is made up of a number of orbitals. Now that orbital is kind of a confusing concept, but think of it as a room or a bed or a seat that somebody can sit in, right? So each of these, let's just call them is a two-person couch. So each orbital can hold 2 people or 2 electrons. And you can use any analogy you want. You can call it Bus seats, you can call it, a bedroom that has two beds or some indication of that. So let's just say that the individual subshell has one room and that each room has two beds and can therefore hold two electrons, and two electrons can sleep in that room. The p orbital has three bedrooms, and each of those bedrooms can then hold two, and therefore each p subshell with three orbitals can hold a total of six electrons. D then has five and can hold 10, and F has seven and can hold 14. So you're just going to use this chart a lot, and eventually you will just remember that P is 6, D is 10, and we won't use F very much. S is 2. The other thing you're going to need to know, and this is kind of one of those memorizing things for now, is that you're going to need to know the orbital filling order. And these are based on lowest energy to highest energy. So this is your low energy, and this is your high energy, and they follow that line. Now, the reason why they follow a particular order is a bit outside the scope of this class. But this is the order that you'll need to remember. They start out relatively straightforward. Shell number one, subshell S, is then called 1s, and that's how you would name it. Shell number two, subshell S, is 2s. And then after 2s, you get 2p. And they follow fairly straightforward. Next one would be 3s, and then 3p. And you can see 3s, 3p. But what gets weird is right here where they start jumping. The 4s orbital actually has less energy than the 3d. And so this is where you really just have to write it down. So the order becomes 1s, 2s, 2p, 3s, 3p, and then 4s, and then back up to 3d. So this is one of those things that you should just write down in your notes, unless you can figure out how you use this squiggly pattern, which I know some people do like. So this is just the information you're going to need in order for us to create orbital diagrams. And I'll explain to you how, but I just want to make sure you understand what this chart says and remind you of what's going on. Let's go ahead and start with our electron configurations. So the electron configuration is simply the address of where the particular electrons are going to be living. So you're going to be taking all of the electrons that are in each element and you have to put them in to the individual subshells and orbitals in order of energy. And so what'll happen is you'll keep adding floors to your house as you add more electrons. It's going to be a single story house for small things, but as you start building, adding more and more of these electrons, you'll have to add more and more of these shells and levels to make room for each individual electron, right? So just to indicate kind of the idea that we know the 1s shell, which is the outermost one, can hold two electrons, and therefore it will be full as you build into those outer shells. It'll hold more electrons, but then you'll have to add more shells as more electrons are added. Let's just do some examples because I think that's the easiest way to get the idea. As you start with the periodic table, and we'll start with the first element, which is hydrogen. Now, first thing we're going to need to note is how many electrons does this individual atom have? And the way you get to that is you will look at your periodic table and you'll see that it has an atomic number of 1. Now, if the atomic number is equal to 1, and this is neutral, as in it's not an ion, we know that that atomic number is equal to the number of protons, and for a neutral atom, number of protons is equal to number of electrons. If it is an ion, you would need to make an adjustment to the number of electrons that you start with. So therefore, we know that hydrogen has one electron. And I'm just going to put it there to start with. So we have to say, where does that one electron go? But what you do is you come back to the filling order. And we know that the very first orbital that has to be filled is 1s. So we're going to write that down. And how you do that is you just write it down. 1s. That's the first orbital that has to be filled. It can hold up to two electrons, but we only have one. And we specify that by putting a superscript of 1s. So therefore, the electron configuration of hydrogen is 1s1. And that tells us that there's one electron filling the lowermost energy orbital. Now, jumping to the next one of helium, which has an atomic number of 2, and you can see that from the periodic table. It is neutral, therefore you have 2 electrons. Let's go ahead and put those in there. We know the lowest energy lowest energy subshell is 1s, but we know from our list that it can hold up to 2 electrons. So we now know both of them can go in there. We've now put 1s2, it is full, and you now have the electron configuration of helium. Jumping down to the next one, which would be lithium, and I can tell you that that's number 3. In it has three, because this is not the lithium ion and this is just the lithium atom, we're just going to assume that it has three electrons because it's neutral. If it was a lithium ion, we'd have to make an adjustment to the number of electrons. We would then say, okay, let's start with what we know. We know that the first shell would be the 1s, and we get to put two in there. So we've got two used up and we have one left. So then we've got to say what else happens after that. Well, from 1s, then you go to 2s, 2s, and we know that all s orbitals will only hold two electrons. It can hold two electrons, but you only have one left, so we're going to put it there. We now know that the electron configuration of lithium is 1s2, 2s1, and that's how you would write it. And you can count. 2 plus 1 is 3. That equals the number of electrons, and so you know you've done it right. Jumping ahead to another thing. We've done hydrogen, we've done helium, we've done lithium. Now let's jump ahead to boron, which is number 5. Boron has an atomic number of 5, and we know that because it's neutral, the number of electrons must also equal 5. So we're just going to do the same thing we did for all the other ones, and we're going to fill them in order of energy. We know we have 1s as the first one because it tells us here. The next, and we know that it can hold two. We also know that the next one would be 2s, and it can hold two. So we've used up 4 so far. Okay, so we got 5 electrons to start with. We have 4, but we now have one left. So what comes after the 2s, right? So you have 1s and the 1s, and then the 2s, the next one would be 2p. So we're going to write down 2p. We can see from our list that the P's can hold 6, but we don't need it to because we only have one left. So we'll put that there. And that tells us the electron configuration of boron is 1s2, 2s2, and 2p1. Okay, let's see what else. So we've gone ahead and we've done boron. Let's go ahead and look at oxygen a little bit further down. Oxygen has an atomic number of 8. Oxygen, let's just write that down. Z equals 8. We know that it's neutral, therefore electrons equal 8. So we're going to go ahead and do just what we've done before. We know from looking at boron that we already know the order they are in. We know 1s2, and it held 5, so we know we can start there. That's the first two. Then we know 2 more go into the 2s. We now have 4. And then we say, okay, well, we're full at 4. We have 4 left. The next one is going to be 2p. But recall that the 2p actually can hold 6 and not 2. So you have enough room in there to put the remaining 4. So your electron configuration becomes 1s2, 2s2, 2p4, and it isn't full. Jumping ahead to another one, let's see where we are. We're going to go ahead and look at neon. Neon has an atomic number of 10. It is neutrally charged, and therefore electrons is equal to 10. We're going to go ahead and follow the same guidelines we had up here, so I don't have to keep going back and forth. We know that 1s fills up with 2. That's 2 electrons. We know 2s fills up with 2. That's 4 electrons. And we know the next one would be 2p. Okay, so we've got 2 plus 4, 4 minus, and we have 6 left. But guess what? The p orbital can hold up to 6, so therefore all 6 of them can go in there. And therefore the the electron configuration of neon is 2s2, 1s2, 2s2, 2p6, and we would then count 6, 7, 8, 9, 10, and that counts what we have there, so we know that we're all there. Now, the thing to note on this one, and we talked a little bit about these noble gases being particularly stable and non-reactive. So notice they're all the way over here, and I want you to notice something. As we talked about this 1s shell holding 2, you notice that helium was filled that entire 1s, and it's in this line. The other thing to note is that when you got to neon, it went 2s2, 2p6. And so if you look at what's in the 2 shell, it has s's and p's. The entire 2 shell is filled with all of the electrons. And so this having the outermost shell, as they call it, the one on the outside, is completely filled with electrons. Neon is very stable and it's considered a noble gas, as is helium with its full shell of 1. So the whole 1 shell is filled, and this is called a noble gas. And this is also called a noble gas. And they are very stable because that outermost shell, the outermost shell being the 2, the latest one, is completely full, and that is why they're most stable. Okay, jumping to the next idea, let's go ahead and look at magnesium, which has an atomic number of 12. So magnesium has a atomic number of 12. It is not charged, therefore the number of electrons is also equal to 12. We're going to go ahead and look at them in order, and the order is here so I don't have to go back. We know that 1s2, 2s2, 2p6 gives us 6, 7, 8, 9, 10. So that gives us 10, and that would then, we know that the first 10 are going to go there. Then we come back and we say what comes after 2p. What comes after 2p is 3s, so we would then have to put 3s down, and we know that s orbitals hold 2 electrons, and so therefore we can put them there. And this was messy, so let me try it again. 2s2, 2p6, 3s2, and you count 2, 4, 10, 12. You know you have a total of 12 electrons, and it fills, and this is therefore the electron configuration for magnesium. Jumping to another idea, let's go ahead and look at, oh, what the heck? For fun, let's look at phosphorus because it's there. Okay, phosphorus has an atomic number of 15. And we're going to look at phosphorus. Atomic number is equal to 15. Therefore, we have 15 electrons because it is a neutrally charged atom. So we're going to have to put these in order. We already know where the first 12 are going to go. So we're going to start with 1s2, 2s2, 2p6, 3s2. That gets us 12 of them. Okay, because we know that's going to be the same. We'll have 3 left. And what comes after 3s on our list? So from 3s, we go to 3p, and we'll write down our 3p, and we have 3 electrons left that have to go there, and that becomes 3p3. And that is your electron configuration for phosphorus. I did not mean to erase that. We'll undo that. Thank you. Okay. Sometimes the computer gets confused. Okay, so that is the electron configuration for phosphorus. Now let's jump down to something a little bit more tricky, and we're going to look at germanium. So this is where we've followed these in order, and we're going to look at germanium, which is number 32. Okay, so germanium has an atomic number of 32. It is not an ion, it is fully charged, therefore the electrons would be 32. So we're going to put these in. We now can start by following what we already knew, which is 1s2, which is the 1s, then the 2s. It's filled. Then 2p is filled. Then 3s is filled. And where are we? 2, 4, 10, 12. Okay, we've got a whole bunch more. So let's go ahead and look at the 3p. We know 3p can hold 6 because because a p orbital fills up at 6. And so let's see where we are. 2, 4, 10, 12, 18. So we have 18. So where are we? We've got a whole bunch left to go. So let's see what comes after 2p. We go from 2p to 4s. So let's go ahead and do our 4s. We know the s's can hold 2, so that's 2 more. So that's 20. 2, 4, 10, 12, 18, 20. So now we've got 20 and we have 12 left to go. Okay, so let's see where those remaining 12 are going to go. From 4s, we must go to, ooh, that's weird. It doesn't go straight to 4p, it goes to 3d. Ha, let's write that down and see what happens. Okay, so we have 3d, but this is where we have to remember that the d orbitals hold how many? They hold 10. Okay, so we can put 10 electrons into a d orbital. We have 12 left, so we can fill that one up with all 10. Okay, so that's going to give us 10, and we have 2 left. What comes after 3d? We then go to 4p. Okay, so then we're going to write, oops, this should be in a line, but it's not, but I'm running out of room. Oh, there we go. I can actually do that in order. 4p. And we know that p orbitals can hold 6, but we only have two left, so we'll put those two there, and we've now filled that up. So germanium has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4d10, 3p4. Well, that's getting pretty long, isn't it? So we do actually have this thing. We have an abbreviation we can use when these things start to get long. Now, this would be considered a full electron configuration, but we do have this other thing we can do that will allow us to make these a little bit shorter, and it's called noble gas configuration. So if you look for geranium and you say, what was the previous noble gas? Remember this column 8 being the noble gas? You're going to say that was argon. Argon has a electron configuration of 18. So let's go ahead and run that one out. Argon, it's Z equals 18, therefore electrons is equal to 18 because it is uncharged, and we know that we have to get 18 of them in there somewhere in a particular order. 1s is full, 2s is full, 2p is full, 3s is full, 3p is full. And let's count them. I just happen to know the answer. So 2, 4, 10, 12, 18. That is then the noble gas configuration of argon. But here's the thing, if you were to take a look at the noble gas configuration of argon and compare it to the noble gas configuration of germanium, you notice this right here matches this right here. So then you can do is you can actually write the noble gas, you can write the configuration of germanium by putting the noble gas symbol in square brackets. Now, all of this right here is just a shortcut for that. You've now done that, and then all you have to do is add this here to the end over here. And so we're going to go ahead and do that. And that's going to be 4s2, 3d10, 4p2. And you'll see that this is a shorthand. Rather than writing out this entire, this entire long thing, you can do noble gas configurations. But so remember, this is noble gas configuration, and this is the full configuration. Now, do remember, this is super important. On an exam, I may ask you to give me the full configuration. So if I ask you for the full, make sure you give me the entire thing. If I ask you for noble gas, it would then be this truncated one. To look at another example of a noble gas configuration, we can come back up here and see that we can compare our neon on our magnesium. So if you notice up here that the neon is in fact a noble gas, as I specified earlier. It has the configuration of 1s2, 2s2, 2p6. If you compare it to a little further down the periodic table of magnesium, you can see that this part of it right here is the same. Well, that's not exactly what I wanted to do, as neon. So therefore you can write your magnesium electron configuration as square brackets, symbol for neon, because that's just going to represent that. And then you add what's left behind, which is a 3s2. So again, either of these are valid for magnesium. This is noble gas, and this is full. So do make sure you know the difference between the full electron configuration and the noble gas configuration for these different elements, and they could be written in a different way. So just to go back and summarize what we've done, what we've done is we were using this filling order, and we're using the number of electrons per subshell to create these electron configurations by filling in the electrons in order. Again, you're going to need to just memorize this, write it in your notes, or otherwise know it. The same thing with this one, you're going to need to memorize it or write it in your notes. You will not be allowed to use this paper on an exam. You can use it on a quiz, but not an exam. But you'll do need to know those few things and know how to use them. So just doing one final example, just so you can see how it works. I'd like to quickly do an example of a of an of a sorry of an ion. So let's take a look at magnesium. So if we take a look at magnesium, as we recall from um, our ion charts, we know that magnesium naturally wants to be a 2+ ion. Okay, so magnesium's atomic number is 12, right? So we know that Z is equal to 12, but if we recall that when you have an ion, you've given up two electrons. And so in this case, the electrons is actually equal to 10, because we have given up two of our electrons. And so we have two less electrons than we have protons. And we can do the same thing by saying protons plus electrons equals 0 or equals your charge, and basically is how that works. That would be that for a neutral. If you were going to do this the otherwise, you know that you have 12 protons, you know that electrons you don't know, your charge is then plus 2. You could then determine that you must have uh, sorry, minus, that's the wrong, electrons being negatively charged, so this is technically a minus. And you would know that 12 minus 10 equals 2, and then therefore you would have 10 electrons, just to remind you from before. Okay, so now you're dealing with the atomic number not equaling the electrons, but you still would fill them in exactly the same way. So you would say first thing you would do 1s, and you would have 2. Then you would have 2s, and you would have 2. So that's 4, and you have 10, so you have 6 left. Then you know the next thing is going to be your 2p, and you know your 2p can hold 6. So you have 2, 4, 6, 10. So this right here is the electron configuration for the magnesium ion, which holds 2, 6, 7, 8, 9, 10. But I'd like you to recall what the electron configuration was for neon. Okay, so if you go back to it's up there and you can't see it, but let's go ahead and look at neon. Neon had atomic number of 10, which again is the same number of electrons. It is neutral, therefore the electrons is equal to 10. You see the same 10 electrons are going to fill in exactly the same way. And therefore, the electron configuration of neon is exactly the same as the electron configuration of the magnesium 2 plus ion. And this is not by coincidence. If you look at the periodic table, it wants to be the things that become ions will become ions in order to be as close as possible to a noble gas configuration. If you'll notice that the fluorine ion always becomes -1, it gets an extra electron to become like this. And if we looked at the fluorine electron configuration, fluorine individually has 9 electrons. Its neutral would be 9, Z equals 9 or 9 electrons, 1s2, 2s2, 2p, 2, 4, 6. It's -4, you have 5, 2p5, right? So that is not full because it wants to be 6. But if you were to look at the fluorine ion, which has a -1, it now has 10 electrons, and it's going to have a noble gas configuration of 2p6, which again is the same as the neon electron configuration. And so the most stable ion is going to be the one where the electron configuration matches its nearest noble gas. So that's just something to think about and why that happens. So hopefully this has been helpful. I'm going to end this video for now because it's getting pretty long, and I'll do a separate video for the orbital diagrams.